I'm pleased to introduce our first speaker for the session, Professor Rose Amal. Her presentation is called Photocatalysis from Material Design to Engineering Reactor Systems.
Okay, thanks, Jagadish. Good morning. It is a great pleasure and honor to be here today. I'd like to thank the Australian Academy of Science for giving me this opportunity and electing me to be a fellow of the Academy, and also thanks to my colleagues who supported my nomination and nominated me. So for the next 12 minutes, I'd like to share with you my work in photocatalysis from material design to system engineering, a research areas that I have been working on for over 15 years. So first is, what is photocatalysis? Photocatalysis is a process that uses light in order to activate catalysts, in order to initiate chemical reactions. And the reasons is of great interest and also why I got into the field is because you can use sun irradiations in order to, as the light source. So it's a process, it's a green process, renewable process that you can harness solar energy and convert it to chemical energy and store as chemical energy. And another reason is because it has many different practical applications. Some of them has been already put in practice. It's ranged from for environment applications to energy applications, for water treatment, air purifications, chemical synthesis, organic synthesis, and potential use for hydrogen generations and CO2 conversions. So how does actually a photocatalyst work? So when you have a photocatalyst, which is normally a semiconductor materials, when you hit it with photon with energy greater than the bandgap energy of the semiconductors, you excite the electron from the valence band to conduction band, leaving these holes that is highly oxidizing. So if you have organic molecules that's in contact with the holes, it's readily oxidized, ideally to carbon dioxide. And the excited electrons then will be scavenged by if you have oxygens in the environment. But if you don't, and if you want to use the electron for other reactions, for example, for hydrogen generations, so the intended electron then will use to react the proton to produce hydrogen. Whether you use the electrons for the reactions or if you want to use the holes for the oxidations, the most important thing is that you need to make sure that the electron and holes are captured by the targeted molecules very quickly. Because if not, then if they recombine, there's no reactions. And this is critical in designing a good photocatalyst. Therefore, that if you look at that process, the process depends on the photocatalyst properties, the electronic properties, the optical properties, the physical and chemical properties. Also, it's important to understand what's happening on the surface as well. The surface reactions is very critical. And last, it's important to have the light. If there's no light, even if you get 100% photonic efficiency materials, you will not have any reactions. Saying that, a lot of the research for the last 2 decades mainly concentrate in material design. More than 85% of journal papers in photocatalysis for that period is only making materials, without much about understanding what's going on the surface and without much about the process system. So my contributions in the field is to join the dots and link these three together. Is understanding what's going on the surface, and then understanding what's needed in the process system, then engineers the materials for the appropriate applications. So when we want to design the photocatalyst, one thing that we want to achieve is that we want a high photonic efficiency catalyst. That is the critical part. That is the overall aim of the design. To do that, we need to make sure that the catalysts that we design have minimal holes and electron recombinations, because as I mentioned before, if they recombine, there's no reactions. We also want the charge that is excited to be able to be captured by the molecule as quickly as possible. So that is part of this design. Last, because we want to use it for solar irradiation, so we want the catalyst to be able to absorb the wide solar spectrum. A lot of the photocatalysts available nowadays only can be activated by the UV light. So that is part of the work that I'm doing. And in my lab, we have a range of synthesis techniques. We have the flame synthesis, the ionization method, hydrothermal precipitation. And to synthesize, design a range of semiconductor materials a range of metal oxide, perovskite materials such as bismuth vanadate and strontium titanate. But the overall goal is to, using bottom-up approach, to control the morphology as well as the crystal structures to be able to have the highest photonic efficiency. So, one of the examples I wanted to illustrate today is that in search of high photonic efficiency catalysts, we found that these layer structures molybdenum oxide that we initially intend just for our photocatalysis application have so-called self-photochargeability. What does it mean? As I explained before, when a photocatalyst, if you illuminate with light, it will generate excited electrons. But with this layer structure molybdenum oxide, it has another extra properties, because what happens is that during the illumination, if you have alkali cations in the solution, the alkali cations will also trap the excited electrons. When it's trapped, that means that it can store this electron in the materials. And one of the things that we use for these materials is for photoelectrochemical processes. The difference between photoelectrochemical processes is that you need electrical bias in order to start the reactions. So normally, when you have a normal photocatalyst materials, when you carry out the reactions, you have electron going to the cathode sides to perform the reactions, intended reactions, for example, hydrogen generations. But with these materials, because it can store the electrons, what happens is that when you illuminate, when the illumination is suspended, when you stop the lighting, normally there is no reactions. But because these materials can also store electrons, when the light is off, the electron can still go to the cathode to perform the reactions. So, which means that this particular materials has dual functions and has potential application for solar technology, because as we know that solar technology, when there is no sunlight, there is no reactions. So with these dual functions, it can harness the solar energy, excite the electron, and then store the electrons. And when the light is off, when there's no sun, it can still do the reactions. Okay. So with the material design, one of the things that is important, which is people normally just stop in the designing and get the high photonic efficient materials, is that we need to understand why we want to use this photocatalyst for. What is the application? What's the targeted applications? So for example, if we want to use this catalyst to oxidize organic, the hole's energy, the hole's potentials are critical. We need to make sure that we design the catalyst that has enough energy to be able to degrade the organic. And if for water applications or air purifications applications, you want them to be degraded to carbon dioxide. You don't want them to be degraded to another organic products that might not be the desired products. So in terms of the designing that, you need to know what you can get. And even you can get a photocatalyst that can completely degrade the organic to carbon dioxide, but in real practice, in water treatment, for example, you might need to handle 1,000 liters, megaliters of water per day. And the kinetics is also important. So not just the thermodynamics, so the kinetic is critical. And with natural organic matters that you may normally find in surface water, they have phenolic group, carboxylic group, hydrophobic fractions, hydrophilic fractions. It's very, very complicated. So a lot of the time that if you put this process in water treatment, you can degrade the organic to smaller molecules, but you might not be able to completely mineralize it with the limitations of the time. So knowing the limitations of the system then, my group is using the photocatalysis, redesigning the process system, using the photocatalysis not as an on-light treatment to treat the water, but using the photocatalysis as an off-site regeneration system. So we designed materials, a photocatalyst, that is highly absorptive. So we have to make sure that the surface can capture the natural organic matters very quickly in large quantity. And after that, because of the magnetic properties of the particles, we can really recover the photocatalyst and particles very quickly. And because of the photocatalytic abilities of these materials then, we can regenerate it using sunlight. And we do not have that limitations that we need to do it very quickly, because you can just put the catalyst and sunbathing it for a longer period of time to completely degrade the organic that's attached onto the surface of these particles. And then after that, then you can recycle, reuse it in the process again. So you actually solve the problem is that you need to have a very fast kinetics in the process by engineers the process system so that you use the photocatalyst as an offsite regeneration process. Another thing that's important in system design is light. We need to make sure that we have uniform illuminations in the reactor system. Without light, there is no reactions. Therefore, it's very critical. And one of the work that we're doing show that the importance of the uniform illuminations is that with the uniform illuminations, you can really suppress the formations of degradation products about 10 times. I think I'm running out of time, so I'll sum up. So what I'll show you is that to design photocatalysts is very critical, especially for hydrogen generations and CO2 conversion, which I didn't really cover today. But that is very critical to get a high photonic efficiency materials. But it shouldn't be done in isolations. We need to really understand what's going on the surface in order to link it to come up with the right materials. In water treatment and air purifications, actually, materials design photocatalyst is not the bottleneck. The bottleneck is the process system. So we need to understand what's going on in the process to be able to come up with the right design. So my contributions in the fields is that by understanding the science, I'm able to develop new materials and also engineer the right process system to bring the photocatalysis into real applications. I'd like to use this opportunity to thank the great support that I have received throughout my careers, my mentor, my colleagues, my collaborators from academia and industry, my research team, the past and present members of the Particle Catalysis Research Group, my family, my husband and my 2 children, Tara and Ari. They cannot be here today. And also, I'd like to acknowledge the funding from Australian Research Council for the last 15 years to support my research. And last but not least, I'd like to thank my University of New South Wales, for giving me a home for my research activities for over 20 years. Thank you very much.
Thank you, Rose. Are there any questions or comments to Rose? Maybe let me start off. And how efficient these photocatalysts are, Rose, and then how do you see that, how can one improve those efficiencies, because that's one of the major challenges in the photocatalysis.
Yep. Well, in hydrogen generations, the photonic efficiency is still pretty low. We're talking about quantum efficiency only a few percent. And in order to bring that to be a real practical application for hydrogen generation, you need to go up to about 10% or more. So it's still a lot of challenge in the design of the catalyst. For water treatment part, it's the process system, it's the limitations. I think that we get the materials already, but we really need to know what's the limitations in the process.
Are there any further questions or comments? Please go ahead, Ross.
Just to repeat the question, could you show the slide on photon efficiency that you're about to show when you ran out of time?
All right. In this particular work, what we did was that we're looking at 2 different types of light source, the same energy input, and we have the blue light black lamp and also LED that will give a uniform irradiations. By giving uniform irradiations with the same energy input, the same photocatalyst, you can see that you suppress the byproducts. That if you don't use the uniform irradiation, you have 70 ppm of acetaldehyde. By using uniform illuminations, you suppress it down to 5 ppm.
Are there any further? Tony, can you please use the microphone, all of you, those who are asking the questions, please, because it's been recorded.
Tony Klein, University of Melbourne. Seeing that acetaldehyde causes hangovers, can you use this illumination to get the benefits of ethanol without the disadvantages of hangovers?
Well, the UV, I mean, if you're using UV light, there will be other effects as well. But I guess that one of the things I want to show here is that you know, when the process is actually to degrade ethanol, but if you don't do it properly, you actually produce hangover gases, the acetaldehyde, and it's quite important to suppress that in the process to make sure that we don't generate those gases.
Okay. Are there any further questions? If not, could you please join me to thank Professor Rose Amal for accommodating the talk?